Welcome to The Explainer. Today, we're diving into the absolutely incredible story of vaccines. And believe me, it's a wild ride that takes us from, get this, ancient folk remedies, all the way to cutting-edge genetic technology.
So think about this for a second. How did we get from a really dangerous ancient folk practice to the kind of precise genetic tech that let us create a vaccine in less than a year? Well, to figure that out, we've got to go way, way back to a simple observation made thousands of years ago. This is a story about human ingenuity, about taking big risks and just that relentless drive to beat disease.
And look at this. This comparison just says it all, right? It perfectly captures the insane leap in technology we're going to talk about. We're literally going on a journey from powdered scabs to pure programmable genetic code. It's a jump from crude biological stuff to, well, pure information.
All right, so let's start with this ancient and pretty risky idea.
You know, the core concept of immunity, it's not new at all. I mean, we're talking about something people noticed over 2,000 years ago. So picture this, Athens, 429 BCE. There's a devastating plague, and the Greek historian Thucydides, he's watching all this unfold, and he notices something amazing. The people who got sick and survived, they didn't get it again. They could actually take care of the sick without any fear. He realized the human body could, well, it could learn.
Okay, so for centuries, that single observation led to this incredibly risky practice called variolation. And the methods were, let's just say, intense. In China, they were inhaling powdered smallpox scabs. In India, they'd rub smallpox stuff into cuts on the skin. It was an absolute gamble, a high-stakes roll of the dice. Sure, you might get immunity, or you might get a full-blown, deadly case of smallpox. Not great odds.
So, how do you go from a terrifying gamble like that to actual science? Well, the answer comes from a really sharp observation, this time in the English countryside. See, the key problem with variolation was simple. You were using the real deal, the actual deadly smallpox virus. So the idea was kind of right, expose someone to the disease to build immunity, but the tool, it was just way too dangerous and unpredictable. The real breakthrough would have to be finding a much, much safer way to do it. And that brings us to Edward Jenner. In the late 1700s, this English doctor noticed something kind of weird, but fascinating. He saw that the local milkmaids, they'd often get this mild disease from cows called cowpox. But here's the kicker. They almost never got the deadly smallpox that was wiping everyone else out. So, in 1796, Jenner decides to test his big idea. He takes an 8-year-old boy, James Phipps, and inoculates him with stuff from a cowpox sore. And then, later, and this is the really tense part, he exposes the boy to smallpox. And what happened? Nothing. The boy was totally fine. And that was it. That was the breakthrough. Using a related but way weaker virus to protect against a more dangerous one, that's the moment modern vaccination was born. Now, Jenner's discovery was absolutely revolutionary. But here's the thing, he didn't actually know why it worked. He just knew it did. The next big leap would require understanding that invisible world of germs. And for that, we have to thank the brilliant French scientist, Louis Pasteur. Pasteur basically unlocked the germ code. He realized you didn't even need a different virus, like cowpox. You could take the actual pathogen, the bad guy, and just weaken it in the lab. He called this attenuation. And suddenly, you had a reliable, repeatable way to make vaccines that were safe, but still effective. This is how we got vaccines for things like chicken cholera, anthrax, and even rabies. Oh, and by the way, he's the one who came up with the word vaccine to honor Jenner's original work. And Pasteur's work, man, it just blew the doors wide open. The whole field just exploded. You had guys like Robert Koch finally isolating the specific germs that cause specific diseases. And then Emil von Behring won the first Nobel Prize in medicine for developing antitoxins for diphtheria. We were finally moving from a shotgun approach to like a laser-guided missile, targeting diseases with incredible precision. Okay, so the science is there. The principles are established. So the 20th century, that was all about scale. It was about building a whole arsenal of vaccines to fight infectious diseases on a global level. And this is where we see a few different strategies emerge for how to train the immune system. You had, for example, the killed pathogen approach. That's what Jonas Salk did with his polio vaccine in 1955, just use a dead version of the virus. Then you had the weakened pathogen. That was Albert Sabin's famous oral polio vaccine. Same virus, but alive and just really, really wimpy. And then, as technology got better, we figured out we don't even need the whole virus at all. We could just use a single piece of it, like a protein from its surface. Super smart. And a lot of this progress was pushed forward by these absolutely brilliant, tireless scientists. People like Maurice Hilleman. You've probably never heard of him, which is crazy because this one guy developed or co-developed more than 40 vaccines. 40! That includes the MMR vaccine for measles, mumps, and rubella that pretty much everyone gets. I mean, it is no exaggeration to say he probably saved more lives than any other single scientist in the entire 20th century. Just wow.
All right, so that brings us right up to the modern era. And here, the technology takes another massive leap. We're talking about moving beyond using the pathogen itself, or even pieces of it, to using its genetic blueprint, its instruction manual. And the breakthroughs in the 21st century have just been staggering. I mean, in 2006, we got the HPV vaccine, which was the first vaccine ever designed specifically to prevent cancer. That's a game changer. And then, of course, in 2020, the whole world watched as mRNA vaccines were developed for COVID-19 at a speed that it shattered every record in history. It wasn't even close. So what is this mRNA technology? Well, it's a completely different way of thinking, pioneered by researchers like Catalin Carrico and Drew Weissman. Instead of making a piece of a virus in some giant factory and then injecting it into you, mRNA vaccines give your own cells the genetic code, the blueprint. It's a temporary recipe that tells your cells, hey, build this one harmless little piece of the virus. And they do. So your body becomes its own little vaccine factory, training your immune system from the inside out. It's brilliant.
So let's just recap this whole journey. When you look at this timeline, it all makes perfect sense. It's a clear, logical progression. We started with the whole live, dangerous virus, then we moved to a related but weaker virus, then a scientifically weakened virus, then a completely killed virus, then just a piece of the virus. And now we're just using the genetic blueprint for that piece. Each step is a move towards being more precise, safer, and a heck of a lot faster.
It's just an incredible story of human ingenuity, right? We went from powdered scabs to literally programmable genetic code in just a few centuries. Which leaves us with one final, really interesting question to chew on. What's the next breakthrough going to look like?